Okay, so I believe today is the 7th lecture in our course on quantum mechanics 1. And so before I begin, are there any questions from the previous lectures?
Sir, I have a question. Sorry, last class একটা ইয়ে ছিল যে শ্রোডিঞ্জার ইকুয়েশন সলভ করে এমন একটা L2 ফাংশন বা L স্কয়ার ফাংশনের নর্ম হচ্ছে কনস্ট্যান্ট ইন টাইম হবে যদি কোনো সোর্স বা সিঙ্ক না থাকে। তো
Correct.
তাহলে বোর্ন ইন্টারপ্রিটেশনের অনুযায়ী যে আমরা প্রবাবিলিটি মানে একটা ইয়ে ছিল না যে পি পি হচ্ছে যে ওই ওইটা নর্মের স্কয়ার হিসেবে ইয়ে করছিলাম যে পি
Probability
একটা
density.
স্পেস আর পি, হ্যাঁ, ডেনসিটি যেটা হচ্ছে যে স্পেস আর টাইমের ফাংশন হিসেবে ইয়ে করছিল ওটা হচ্ছে
Like this object, right?
ইয়েস স্যার। তো তাহলে মানে নর্ম এটা নর্ম তো কনস্ট্যান্ট বলা হচ্ছে যে যদি এখানে সাই একটা এল স্কয়ার ফাংশন হয়, তো তাহলে তাহলে কি মানে প্রবাবিলিটি ও টাইমের ইয়েতে মানে কনস্ট্যান্ট থাকবে, মানে এমন হতে পারে না যে
No,
ওই পার্টিকেলটা
this is what we call
ওই
rho, the probability density. So
মানে
it can change with time, right? I mean, it can change with space as well, but if it changes with time, then a change of the probability density with time is given by the divergence of the probability current density. Does that make sense?
ইয়েস স্যার, মানে লাস্ট ক্লাসে, হ্যাঁ, এটা লাস্টের সেকশনে এটা
So
ছিল।
I'm not sure I'm getting your question. What's your question again? But whether this is
কোয়েশ্চেনটা ছিল
constant?
যে মানে সিঙ্ক আর সোর্স যদি না থাকে তাহলে এই যে মানে সাই সাই এর নর্ম স্কয়ার যেটা ওটা কনস্ট্যান্ট হবে না মানে?
No. Yeah, norm would be constant, but this is not the norm. The norm is this. So this superficially looks like it should depend on time. This is superficial. Now, if this thing is L2 integrable, that means that this thing will go to 0 rapidly as we go to infinity. And that means that the rate of change of n with respect to time is 0. Okay, that's what we proved.
অলরাইট স্যার, এখন বুঝতে পারছি।
Yeah.
আমি
But that does not mean the density is constant, because this thing is nothing but d cubed x of rho of x of t. So the thing about the Klein-Gordon equation is that the Klein-Gordon equation also it also gives us a equation. It gives us an equation of continuity, right? So the equation of continuity is essentially this: some current density. But for the Klein-Gordon equation, rho is given by some constant times psi star, the time derivative of psi, minus psi, time derivative of psi star. And unlike the rho, that we get from the Schrodinger equation, this is not, rho is not positive density. Positive definite is not positive definite, right? In the Klein-Gordon case. So we cannot give the wave function an interpretation, the same interpretation as we do for the non-relativistic case where we have the Schrodinger equation, right? So, I mean, the Klein-Gordon equation does have interpretation as a quantum field theoretic equation. In that case, what will happen is that rho is going to be related to, this will be related to the charge density. And in that case, this equation, its expectation value will be related to the conservation of charge. But that's a quantum field theoretic interpretation, not a quantum mechanical interpretation. And the reason why for the Klein-Gordon equation, rho is not positive definite is because the Klein-Gordon equation is second order. Order in time. Okay. If the Klein-Gordon equation were first order in time, then the reason why we get a positive definite charge density for the Schrodinger equation is because it's a first order in time. And that's really what motivated Dirac to look for a relativistic wave equation which was first order in time. But we know, from our tutorial that that's a big challenge because first order in time equations, wave equations do not respect the isotropy of space. So the way that Dirac got around it is that he wrote down a first order in time equation, but what he said is that instead of the coefficients being numbers, he said that let the coefficients be matrices. Okay, so and he had like I think a mass term. Yeah. On dimensional grounds, this is mass, not mass squared. So the way Dirac got around the problem of having an equation that does not respect the isotropy of space-time is that he said that, these things are matrices, that is, they don't commute. Okay, and then what Dirac, but this is very general, what is alpha and beta? Dirac said, okay, what if he squared this equation? So he found a way to square this equation, basically apply to it, this matrix, I think, something like this. And then he found an equation which was second order in time. And he said that that equation should be the Klein-Gordon equation. And that way he found that these matrices, alphas and betas, have to satisfy a very particular algebra, which is now called as the Dirac algebra. And it turns out that this algebra was discovered before by a mathematician, and that's in mathematics, it was known as the Clifford algebra. Okay, so that's a story for another day. Okay, so any more questions from previous classes? Okay, just give me 1 second, okay? I'll be back in a second. Okay, so what are we doing today? So Schrodinger equation is a wave equation. Okay. So Schrodinger or Schrodinger, you can pronounce it both ways. Equation is a linear wave equation. Okay. In a future tutorial, we shall explore an example, a famous example of a nonlinear wave equation, the KdV equation. So whenever we have linear waves or linear waveforms, do you know of any applications where any real life situation where there are lots of analysis of linear waveforms?
Signal processing.
Signal processing, exactly. Acoustics. I mean, acoustics is not exactly, it's not those, those instruments are pesky. They're not always linear, but, we like to be in the linear regime where things are predictable, right? So whenever we have a linear waveform, yeah, the tool for analyzing linear waves is Fourier analysis. Fourier analysis. Okay, so we have to review Fourier analysis. Now, how many of you had some introduction to Fourier analysis?
I had some, but not much.
Okay,
I
Shujash
did
had one.
in math, linear algebra, or complex course.
Okay, Farhan had some.
I've had also in like context of other things, but not directly.
Okay,
That was what we were learning.
Saif has had. Who else?
I had it complex.
Okay, good. Dipro had it. Anyone else? Okay, so a lot of you haven't had Fourier analysis. So although I cannot, like, Fourier analysis should be half of a whole course of either analysis or advanced linear algebra, so I can't really do that. So I will do a review of Fourier analysis, but I will basically try to make it independent. Of course, it won't be anything rigorous. So yeah, that's it. So we are going to do a review of Fourier analysis. Now, the word linear should be, should be important. It should be ringing some bells here, because Fourier analysis deals with linear systems. That means that the underlying ideas of Fourier analysis are from linear algebra. So Fourier analysis is the marriage of linear algebra. In linear algebra, we deal with matrices, right? And they're usually finite dimensional, say n by n matrices. And these matrices act on vectors, right? And they're usually column matrices n dimensional. Okay, and then we have to find eigenvalues of these matrices, right? But the vector spaces in linear algebra are usually finite dimensional. if for some reason n goes to infinity, then we have to say worry about additional issues. So for example, if I had a vector v, which was a sum of, say, n vectors, say alpha I, and then say ei. Ei is being the basis vectors, okay? Then, alpha i's could be any numbers, any complex number, right? If you're dealing with a vector space over the complex numbers. So, it doesn't matter what alpha I is. When we say, okay, I take the modulus of V, all I have to do is I have to just, I just have to calculate this, right? Sum over I, 1 to n. And that's going to be a finite number. But if, for example, n goes to infinity, then we have an infinite number of terms here suddenly. And then we have to worry about, issues of convergence, okay? So in Fourier analysis, those ideas are important. Although, we are not doing an analysis course here, so we won't go into the nitty-gritty of those things in a very rigorous manner, but we will address those things in a heuristic manner. So, just as in linear algebra, we have matrices. Now, what are matrices? Matrices are maps from your vector space to itself, right? That's what matrices are. So in analysis, in Fourier analysis, what will happen is the vectors will be replaced by the space of functions, the space of, say, L2 functions. I don't know if this is the right notation. I'm just making it up. So the linear operators that map you from this space to itself, okay, so it's an endomorphism, will be given by linear differential operators, okay? So, so matrices in Fourier analysis and in quantum mechanics are basically generalized to linear differential equation. So, for example, we will see that del squared is a linear differential operator. D by dt. I times, say, the gradient operator, etc. I'm just being very, very vague here. So we shall meet these things. Okay. So for now, I'm just going to we are going to develop Fourier analysis, and later on we will see that Fourier analysis has deep connection with the axiomatic structure of quantum mechanics. Okay. So after we have done a bit of quantum mechanics, we will stop and we will reformulate quantum mechanics as an axiomatic systems, and we will make connection to Fourier analysis. Okay.